Conceptual mathematics exemplified by non-traditional lines and planes problems. You have an abstract. If you're attending live at this webinar, you've read the abstract, but there it is for anyone who comes to the recording of this webinar later. Let me give you an overview of what I'm trying to accomplish by that abstract and by this webinar. Some 10 years ago in MaplePrimes, there appeared a series of non-standard lines and planes problems. These were problems that you would not find in the typical calculus book where lines and planes are used in the first unit on vectors, lines, and planes. And these problems taxed my imagination, and they forced me to think really hard. They were not easy. Eventually, I crafted solutions with the different Maple tools, and I even incorporated those solutions in my suite of clickable calculus exercises. Now, in today's webinar, I want to look at these problems from the perspective of the conceptualization that it takes to solve them. Now, I'm going to try to show how I thought out the solutions, then using tools in Maple, implemented those solutions as I conceptualized them. Now, quick glimpse of what I'm trying to say. Suppose I needed a line perpendicular to another line. Well, I would use the projection and line commands in the student multivariate calculus package. That would provide what I needed. No need for writing or solving equations. It would be like you got these smart speaker things. Alexa, get me the perpendicular from point A to the line to points B and C. No manipulation of the data, line and equations and solving equations and so forth. So that's the kind of thinking I want to demonstrate. Let's see how this idea plays out by means of some examples. Let's look at some of these exercises. Here's a very first one. Obtain an equation for lambda, the line that passes through the point A. Okay, a line through A, and it intersects a line L and is also parallel to a plane. Line through A intersects line L and is parallel to P. What has been given? What is to be found? Let's take a look at that. So we go over here to a page where this problem can be solved. Here you have a restatement of the problem, and here is a link to the original post, modified slightly so we don't run into copyright issues. So here's a figure, and click this button here to redraw the figure. This gray plane is the plane P. That's the given plane. The line we're looking for is parallel to that plane, so it lies in a parallel plane. That's what this pink thing is. It's a plane parallel to the given plane. So here's this line through A. It intersects this red line, which is the line L. Okay, so this point and this point, this is the given point. A line has to pass through it, has to lie in this pink plane. The pink plane is parallel to the gray plane, and it intersects this red line. But the red line has to intersect the pink plane too, and that's how you get your second point on the line. So let's implement that thinking. Bring in the student multivariate calculus package and define point A, the given plane P, and the given line L. So we need to get this pink plane, the parallel plane. Now that parallel plane contains the point A, and its normal is the same as the normal on P. So there's the normal on plane P. It's the same as the normal for this plane Q, the pink plane. And then we want to get the intersection of the given line with this pink plane. So we get the intersection. There it is. We need to form the line from A to B or through A and B. So line, and then we ask for a representation, and the form that we want to see is this. You can think of this as a vector, position vector, or you can think of it as parametric. This is x, y, and z as functions of t. So a second example. Have a plane. You're looking for a line that lies in that plane. That line we're looking for is perpendicular to this line, and it is also at a distance of 4 units from the point of intersection of the given line with the given plane. I could not picture that immediately. It took a great deal of effort to picture that. So let's go over to this page where we can work on this problem. Again, here is the link to the original form of the problem. So here is a little figure that might help. Pink plane is P. That's the given plane. This vector W, it's actually in gold, is along the line L. Did not draw the line L, but that's the direction of the line L. We have the normal to the plane. From that normal in this vector W, we can, by cross product, get this direction V. V will necessarily lie in the plane. From N and V, cross product, we can get U. It will lie in the plane. This point here is the point of intersection of the line L with the plane. We can find that. If we go out along U, the appropriate distance, we can find this point through which we will draw one version of lambda. We could put another one over here, another one. The direction of lambda will be the direction vector V. And if we can implement that, we would have a solution. So let's implement those thoughts in Maple. Student multivariate calculus package. Define the plane P and the line L. Now, W is the direction vector for a line L. N is the normal for the plane. M is the point of intersection of the given line with the given plane. The vectors V then U are formed from these cross products. And the two lines, only one of which is drawn here, two lines, at the end of U pointing this way and at the end of U pointing that way. This will be the direction for those two lines, V. We've shown that here in the picture, parallel to V. We need a point, and the point is at the end of that vector U. So here we have normalized U, and we have converted that to a list because points are lists. And the displacement 4 is the multiplier, and we add that to M to get the point at the end of the vector where we want to put the line v with direction vector v. And the form of that of the combined vector parameter s, so that you can think of this either as parametric representation or position vector representation. And here are the two lines, one on either side of point M. Let's take a look at a third problem. So problem 3, equation for a line. Okay, so we're looking for the equation of a line. This line is parallel to two planes. So planes P and Q parallel to two planes. And it must intersect two lines. So we have two given lines, two given planes, looking for a line L parallel to both planes, and it intersects two lines. Not obvious to me until I thought very hard about this. So let's see how one could think this out. So go over to this hyperlink here. Here's a statement of the problem linked to the original post. Let's begin thinking out the solution to this problem. So here's this figure. These are the two planes that have been given. They intersect. A line parallel to both planes is necessarily parallel to the line of intersection. So we have a direction for this line. It's the line of intersection of the two planes that gives us this direction vector. Now here are the two given lines, and we have to have an intersection with both these lines. So if we could get the general point here and the general point here, we could figure out intersections. Let's see how we do that. Well, V will call the direction for the line. Get position vectors to these 2 points, generic points on the two given lines L. The difference is a vector W, and we can make that vector W parallel to the line of intersection of the planes if the cross product is 0. So we will solve the equations involved in W cross V equals 0 for the parameter values U and V that satisfy those equations. Then the actual line that we want is take, for example, R1 evaluated at the value of this parameter and add a multiple times V, because V is the direction vector for that line. So let's implement that thought process in Maple. So here's student multivariate calculus package. Define the two planes and define the two lines. Position vector R1 and R2 are position vectors to generic points on the lines L1 and L2. And by doing combined vector form, they are in vector format, so it's position vector. I also need the direction of the line of intersection of the two planes. We call that V. So get intersection of these two planes and get the direction of that line of intersection. We then form R2 minus R1 cross V. We want that to be 0. It's going to go into a solve command. Solve says, okay, if you didn't put the equals 0, it's okay. I understand what you mean. This has to become a list, not a vector. It has to become a list because solve looks for a list of equations. So that's why I convert to list. And although there are 3 equations, we're solving for the 2 parameters, U and V, right? Because U is a parameter on L1 and V is the parameter on L2. If those equations were inconsistent, we'd be out of business here. Equations have to be consistent. We get a u and a v value. We evaluate, for example, position vector r1, which puts us on L1. Evaluate using these two values for the parameters, and plus PV, direction vector. Here is either think of it as parametric or think of it as position vector representation for the line that we're looking for. Now, for a fourth example, we are looking for the equation of a line that lies in a given plane if it, that is this line, is orthogonal to L, given line, and at a distance 3 units from it. Now you've got it over here, and you have it over here. What are the references? Now, my understanding of the English language is that the reference to a pronoun is back to the nearest noun. So the nearest noun is the given line L. So that was part of the problem that I had with this example, trying to figure out just what the wording meant. Let's go over to the hyperlinked page, magnify it. Okay, here's the link to the original post. Let's think out this example. Ultimately, eventually, this figure was necessary. Now, what do we have here? The yellow bit here is the given plane P. Red line is the given line L. Okay, so L and P. Normal to the plane. Project the given line L, the red line, projected to the plane. That's what that green line is. It is the projection of the given line L, the red line, onto the plane. The direction of that green line is vector V. And V cross N will be a vector W. That W lies in plane P, and it will be the direction of the line we're looking for, because the line that we're looking for is orthogonal to the given line. Then the distance between the line we have to find, because that line is going to lie in the plane, that line, black line there, is at a distance of 3 units from the given line, which is the red line. Okay? Okay, let's see how we would implement such a solution in Maple. So, multivariate calculus package, given plane, given line. By projecting the given line onto the given plane, we get the projected line, which is this green line projection. It has a direction vector V. Express the points on that line, which is LP. You get its representation. There would be a vector, position vector, but we make it a list because we want to think of A as a point on this green line. We need the normal to the plane. Cross product of N and V is this goal vector W. which would be the direction then of the black line, which is the line we're looking for. B is the generic projection of points on the green line down to the red line. And we're looking for the point here and the point here for which the distance is 3. So projection, that's B. We get the distance between those 2 points, A and B, set it equal to 3, and solve for the value of the parameter that does that. And there are 2 such values. So if you take point A, which is on the green line, and go back to its vector form, it has parameter t. Set that parameter equal to one of these 2 solution values and add a multiple of the vector w, this is the direction vector. You get this line. You have another choice here. You get the second line. And down here, I've put some of the quantities I did not display as I was working my way down through here in case you want to see what they look like. So here in problem 5, we're looking for 2 lines. They both pass through point A, and they are perpendicular to a given line L. And all we know about the given line L is its direction. And the conditions that determine these 2 lines, lambda A and lambda B, are that the distance of those lines from the point B are respectively a maximum and a minimum. I found that extremely difficult to visualize, and I had to think about that a great deal before I could even begin to tackle that question. So let's go over to the hyperlinked page. And again, here is the link to the original post. See if we can analyze this problem a bit. What are we given? We have a point A and a point B. Is that not right? There's a point A and there's a point B. Direction vector V for a line. So look at this diagram. This is the direction vector V for the line. And these 2 lines that we're looking for are to be perpendicular to the given line whose direction is V. So they must lie in the plane for which V is the normal. Here's the plane for which V is the normal. The lines that we're looking for are in this plane. Now I've drawn these 2 lines, green and blue. They turn out to be the lines we're looking for. But at the moment, the best we can do is to let omega be the generic line that passes through point A, and we've made A lie in this plane because we can move that plane up and down, because all we know about the plane is it's normal. Let it be the generic line, omega is the generic line through A and lying in this plane. And then we compute the distance from B to that generic line and maximize and minimize. But let me point out that this is an animation. And what I'm showing are lines from B to a moving generic line in the plane P. And when it gets to here, you see this green line. You got a projection. That's going to be the minimum. So projection here will give you the minimum. And the maximum distance is going to be when you go straight down to point A. And that's that blue line. So that turned out to be the solution. But believe me, it took quite a bit of thinking to get to the realization that that's what was happening. Let's see if we can now implement this solution. Student multivariate calculus package. What are we given? Points A and B, those are lists, and the direction vector V, and you can see the wedge brackets makes the vector V. We want the plane P, that's this gray thing here. It contains A, and V is its normal. I would like the equation of that plane, so I get the representation, and I put it in the form Z equals. Because the generic line in this plane I've called P will be formed from 2 points. Point A and the generic point on that line which lies in the plane. And so we get that generic point as UV 1 minus 2U plus V, because that's the Z coordinate. Then I want the distance from B to that generic line. Comes out to be very ugly, so I simplify it before I display it, and it requires an assume real. So this is the distance. It's a function of two variables. I want to maximize and minimize. So the maximization and the minimization take place next. To maximize, I use the maximize command, and this option location equals true gives the values of the parameters at which the maximum occurs. And you have a minimize command, minimize, same option. The return here is the maximum value, and this is the location information, and the maximum value is repeated. And here, the minimum value, the location, and a minimum value repeated. So we want to simplify this expression. And you can see there's a 7 times 3 in here, and there's a 7 times 11 here. There's a 7, 3, and then 11. You can see a 33. So root 30, 33, and here I floated it. For the minimum, clean this up, and it's 11 over the square root of 6. If Maple would have left this as 1 over the square root of 6, you see that? And float it. It's smaller than this number. And then now look in here at the values of U and V. There's a value for U, but V is free. There's a value for U in terms of V, and V is free. So now let's make use of that information and find out what the generic line omega turns out to be in each case. So this op, which stands for operand, so you digging into this sequence of two things, and we want this set right here. And to get it, I just experiment to figure out what op I'm looking for. Grabs this set. And I evaluate the generic line omega with this information. And I get the line in a vector format. And I temporize here because after I do that, I want to set v equals 0. Remember, v was arbitrary, so I can set it equal to 0. And the parameter on the line, which was t, I changed to 2s over 3, and it turns out to make this vector be a vector integers. So this is the line for which the distance d is maximized. And over here, we do this parallel computations to get the line for the minimum distance. And again, v equals 0. And here I set the parameter on the line equal to 19s over 3, and that makes everything turn out to be integers. Having done these calculations, I was a tiny bit uneasy still, so I did some verifications. So the first thing I did was project the point B onto this minimizing line, lambda b. So we do a projection B onto this line. And then we want this to be a point. So we have 2 points, B and C. You get the distance, and it turns out to be this number here. So projection is what I said earlier, and it is correct. That's projection and minimization, they go together. What is the distance between A and B? That was maximizing, straight distance, root 33. That makes sense. I drew lambda A and lambda B orthogonal. Are they truly orthogonal? Well, this is the direction vector for lambda A, 3 minus 2 minus 8. This is the direction vector for lambda B, minus 10 minus 19, 1. And the dot product is 0, so those two lines are orthogonal. The sixth problem is not quite as hard as some of the other ones. Looking for the equation of a plane that contains a line. And the determination here is that the distance from the point A to that plane is a maximum. So let's go over to the page in which we can tackle this problem. And again, here is the link to the original form of the problem. So let's do some thinking here. The first thing that struck me was the way to visualize the line and the plane that contains that line, how to look at that. Well, here's some figures over here that I sketched and found useful. That red dot represents the line, the given line. It's drawn perpendicular to the plane of the screen. Now, the plane that contains that line is also looked at on edge. And that's this green line. It's the edge of the plane, finite part of the plane. Now, this is point A. That gold dot is point A. And the dotted red line represents the distance from A to the plane. And the thing that struck me was that the maximum distance appears to be when you have orthogonality here. And this figure came after I had constructed some stuff. This is the point A. That's the line. The point where you get this maximum distance does appear to be the projection. It turned out to be true. And this is a graph of the distance. It does have a maximum. So I said I need to find a plane that contains a line. All right, so that line does not completely determine the plane. The plane can rotate around that line. So I need another point. So what did I do? I just made up a point and stuck it on that plane. and then said, find the distance to the plane, maximize it. So how did I do that? Well, I picked a point 11C. Right? If you have a plane sitting over the XY plane, you pick X is 1, Y is 1, arbitrary. And the unknown is the Z coordinate, and I call that C. So that gave me the point to construct the plane P, and then I could do a distance, and then I could do a maximum. So let's implement this thinking in Maple using student multivariate calculus. These equations are the parametric representation of the given line. Remember here, I could have just copied it from here, given line. Then I form the line object. So L is the line. Then I need the plane P. Well, it contains this line. I need one more point. So I picked that point to be 11C. I define the point A. And I can obtain the distance from A to the plane P as an expression. I simplified it. And this is the expression. That's what I want to maximize. So I use that maximize command we saw earlier. Location equals true gives me the value of the parameter that does the maximizing. So I get the equation for the plane. It has a C in it. I set C equal to 9/2. No fancy referencing, just typed in 9/2. And there were halves running around, so I hit it with a 2 and make the equation have integer coefficients. And that's the equation of the plane that I'm looking for. A little bit of extra insight here. That notion of orthogonality struck me. So I said, let's explore that. This is the plane. Here's its equation. Just drag that over. Form the plane and project A onto that. I get this point. So this is the point. If I just directly project A onto the plane, I would get that. If I project A onto the line L, I would get the same point. And if you remember in this figure, A, the line, the plane, A projected onto the line is A projected onto the plane. So that closed the loop as far as I was concerned. So let's take a look at problem 7. Obtain an equation for a plane. So we're looking for a plane. It contains this point, but the plane has to be perpendicular to this plane and make an angle of pi upon 4 with this other plane. Could not visualize that. Took a long time to think about that. Let's hyperlink over to this page where we can solve the problem. Here's the link to the original post. Let's take a look at what we have to do. So again, using this structure that I learned as a youngster, what are we given? Point M and two planes P1 and P2. What are we looking for? Plane P, it contains point M, and the angle between P and P1 is pi over 2, and the angle between P and P2 is pi over 4. Eventually, what did I figure I would do? Translate the conditions into algebraic equations and solve for the coefficients in a general plane equation. Okay, so it turns out that this is what the picture looks like. Oh, that's clearly the point M. That dot is clearly the point M. To gray plane and the gold plane are the two given planes. The red plane is the one we're looking for. So you notice it's orthogonal here to the gray plane, which is the first one, and it seems to make a 45-degree angle with the gold plane, which is P2. But there's another solution. There's this green plane here, not only the red one, but the green one. And that seems to make a 90-degree angle with the gray plane, and it looks like it makes a 45-degree angle with the gold plane. So let's see if we can do that. The implementation of this solution scheme in Maple starts with loading the student multivariate calculus package. Now, U and V are the normals of planes P1 and P2, but N is the normal of the unknown plane. Not known, so ABC. M is the given point. R is the generic radius vector. P, that's the plane we're looking for. It must contain point M and have normal N, and its representation is this equation. But it turned out that I didn't want to drag along the X, Y, and Z. All I really needed was this right-hand side, which I grabbed here and called little p. This contains the information normal and point M. So then we need plane P1 and plane P2. What is the angle between the unknown plane and plane P1? And what is the angle between the unknown plane and plane P2? Well, these expressions give that angle in terms of A, B, and C. And the reason why there are two of them is because you can measure around one way and you can measure around the other way. What equations do we want to set up? This stuff we'll call little d, because isn't that what you really write down when you write down the equation of a plane? Ax plus by plus cz equals d. Now this op business goes inside here, and it grabs the expression that we want. One is pi upon 2, the other is pi upon 4, and we solve for ABC. There are two solutions, so there are two planes. In this solution, d is the common multiplier. I evaluated q, which is the equation of the unknown plane, with the first solution. So I'm going to have multiples of d. If I multiply by -5 over d, this leading coefficient will be an 8. 8, 6 minus 15z equals -5, so I have integers. And do the same with the second solution. Go back to this equation here, and I'm looking at these numbers, and I'm saying, okay, evaluate q, but multiply the resulting equation by -11 over d. So this drops out. Minus sign goes away. And I have 2x 8y minus 7z equals -11. Two solutions. From the solutions, I was able to draw the picture. Problem 8. This was one of the easier ones to visualize. Talking about a triangle in space. So there's a tilt here. A, B, C are the vertices, and you can see they are each on an axis. Triangle is tilted in space. Neither the geometry package nor the Geom 3D package did very well with this. They want to get the orthocenter of that triangle. Now, the orthocenter is the intersection of the altitudes. The line from the origin to the orthocenter is normal to the plane of the triangle. So let's hyperlink over here to page where we do the work. Again, link to the original post. Pretty straightforward. What you need to do, here's a picture. You see the triangle. You need an altitude. You need another altitude. You get their intersection. That would give you the orthocenter. Then show that the radius vector, position vector, to the orthocenter is normal to the plane. So we want edges, AB, and an edge, BC. You can get the appropriate point you need on that edge by a projection. So you project point C onto line AB, and that would give you the line along which the altitude lives. And then you project A onto edge BC, you get the other line, you intersect those two lines, so you get the coordinates of the orthocenter, and then you show that the position vector to the orthocenter is collinear with the normal. Implementing that strategy in Maple is pretty straightforward. It's not that hard. Multivariate calculus package. ABC are the vertices. They're points, goes to these lists. We form the plane for which those are the vertices, and we get its normal. Lots of ABCs, little ABCs running around, normal. Then we want to project the vertices onto the opposite side for two sides to get altitudes. Okay, so we want to project, for example, A onto the line connecting B and C, so that's the edge BC. You do that projection, you get a point. So you have the point Q1 and the point A, you form the line connecting. So the altitude is along that line. Do the same thing, B projected onto the edge AC. So line AC, projection B onto that, that's a point. You have now 2 points, B and Q2, you get a line lambda 2. You intersect those two lines, and you find the intersection by applying the get intersection command. You make that a vector. It comes back as a list. You make that a vector because you want to show that H, the orthocenter, which is that vector, is collinear with the normal N. And here we do the cross product, and we get the zero vector. Then finally, in order to make sure that I could actually see something concrete, I listed some of the quantities that are hidden up above. This is what the normal looks like. These are the 2 points where the altitudes touch the opposite side. These are the position vector representation of the lines, lambda 1 and lambda 2, that we have to intersect. This is what the orthocenter looks like symbolically. And then I said, let's take A equals 1, B equals 2, C equals 3, and see what these expressions look like. Normal, points on the edges where the altitudes hit. These are the 2 lines along which the altitudes live. And this is where what the orthocenter would be. And finally, let's take a look at problem 9. We have a plane and 2 lines, and here they're given. We're looking for equation of a line L parallel to the plane, but intersecting these 2 lines in such a way as to form between them a segment of a certain length. Even now when I read that, I have to coerce my imagination to visualize what they are talking about here. So let's see if we can think this out and then implement the solution in Maple. So let's hyperlink over to the page where we're going to do the work, magnify things, and here is the link to the original post. I modified to avoid complications with copyrights. Okay, what are we given? Plane and two lines. What are we looking for? A line parallel to the plane, but it intersects the given lines to form a segment of a certain length. So you think this out. What do you want to do here? Suppose you got the generic vector from line 1 to line 2. So you need a point, generic point. You can subtract, or position vector, subtract, and you get the generic vector from one line to the other. Now you got to make it parallel to the plane, so you say v dot n equals 0. But you know what the normal to the plane is because you know what the plane is. So that's one condition. And then the other condition is you make the norm of that vector the required length. This figure was probably drawn after I solved the problem, but it helps if you can see something like this while you're working. So the yellow patch is the plane P. The black and gold lines are L1 and L2. The red and the green lines are the lines that we're looking for. These two red dots have, form a segment of the required length. And these two black dots form a segment of the required length. Neither the red line nor the green line is in the plane. There's a tiny little space between here, but they are parallel to the plane. So let's implement that solution. Student multivariate calculus package. We are given two lines, so let's do something with those. Line, parametric equation, line, parametric equations, and I express the line as a position vector, and I call the little v1, little v2. Big V is the vector between the two lines. To find a plane and get its normal, and we need to solve two equations in the two unknowns t and m. T on one line, m on the other line. V dot n equals 0 is the parallel condition, and norm v equals 3 root 6 is the length condition. There are two solutions, so you have two lines that you'll come up with. Evaluate essentially this difference and this fixed point at one solution, this difference and this fixed point at the other solution. Now I have a lot of hidden quantities here, so let's expose some of them. The position vector representation of two given lines, v1, v2, here they are. The difference, the vector v, the normal to the given plane. These are the two solutions in this sequence S. These are the two lines we are looking for given in radius vector or position vector format. There are a couple of final quantities and verifications that I felt compelled to do. I actually obtained the initial and terminal point for one of those segments and the initial and terminal point for the other segment. So these are the initial and terminal points on the one segment written as position vectors, and I ask for the norm of the difference, 3 root 6. I do the same thing here for the other solution, norm 3 root 6. So that was satisfying. And then the parallelism. So you can see I'm asking R parallel between a line and a plane. And a little bit of the detail here. I'm equating the vector xyz with this omega 1. So I end up with a list of parametric equations, x equals, y equals, z equals. And that allows the line command to form the line. And so the R parallel command can kick in and determine if that line is parallel to that plane. Now I do the same thing over here with the other solution, and in each instance, Maple says parallelism holds.